In this video, I am going to discuss what is meant by a mathematical group. Let us first consider an example. Consider the set of fourth roots of unity. Square roots of unity are well known. They are plus 1 and minus 1. Then what are the fourth roots of unity? They will be plus 1 to the power half and minus 1 to the power half. That is 1 minus 1 I. From this you will get I and minus I, where I is root over minus 1, the imaginary number. Now let us consider a set of these numbers, the set of fourth roots of unity, 1 minus 1, I minus I. And let us consider a rule for combining any two elements of this set. Let that rule be multiplication, just arithmetic multiplication. This is a rule, composition rule, or a binary operation, composition rule. A rule for combining any two elements of the set. In this case, we are considering multiplication. Now, what is the result of multiplying any two members of this set? Consider minus 1 into I. This is minus I. This belongs to S. Minus I belongs to the set S. I into minus I. What is that? This is minus I square. This is equal to plus 1. This also belongs to S. In this way, it will be found that for any two members of S, the product also is a member of S. This property is known as closure property. Closure property. Because you cannot, the set is closed under the operation of multiplication. You cannot go outside this set by using this operation. Let us examine some more interesting properties of this set S. Let us consider the next important property: existence of unique identity element in the set S under multiplication. For any x belonging to the set S, we have x into 1 is equal to 1 into x is equal to x. Where x is any member of the set. For example, 1 into I is equal to I into 1 is equal to I. Thus 1 is such an element that when combined with any other element of the set gives back that element. So 1 is the identity element in the set S if the operation of combining two elements is multiplication. However, I is not an identity element. I into x will give you ix. I into x is not x. Therefore, I is not the identity element in S. I minus 1 minus I are not identity elements of S. Next, therefore, S has a unique identity element. One and only one identity element exists in S. Let us next consider another important property: existence of unique inverse of each element in S. Each element in S can be found to have a unique inverse. For example, I into minus I is equal to minus I square. Minus I square is 1. Since 1 is obtained, 1 is the identity element, Therefore, the inverse of I is minus I, and the inverse of minus I is I. I inverse is minus I, and minus I inverse is I, under the operation of multiplication. Minus 1 into minus 1 is equal to 1, the identity. Therefore, minus 1 is the inverse of itself. Thus, each element of S has its own inverse, which also belongs to S. The inverse also belongs to S. The fourth important property of S is this, associativity. The set S is this, and the operation is multiplication. Take any three elements of the set, say minus 1, I, and minus I. You may combine these three elements in this way. First combine minus 1 with I, and then combine this result with minus I. Your final result will be I squared, that is minus 1. The same three elements can be combined in another way. First combine I with minus I, and combine minus 1 with that result. The result is again I squared, that is minus 1. We see that these two results are the same. So, using three elements, the order of associating the elements is immaterial. This property is called associativity. Associativity. And when all these four properties, closure, existence of unique identity, existence of unique inverse for every element, and associativity, when all these four properties are satisfied by a set S under a given binary operation, then that set is called a group, a mathematical group. So what is the definition of it? Thus S is a mathematical group under multiplication. Now a general definition for a group. General definition of a group. A set S together with a binary operation defined in it. The binary operation is given this general symbol. Is a group if the following four properties hold good. Number one is, for any member X, Y in S, the combination of X and Y belongs to S. This is called closure property. Then there is a unique element E, denoted by E, unique element E in S, such that X combined with E equal to E combined with X equal to X for any X in S. For any member in the set S, there is another element E such that Xe equal to Ex is equal to X. This E is called the identity element of the set. And this E must exist for S to be a group. This is the second property. The third property is this. Each element X in S has a unique inverse, X inverse, which also belongs to X. Every element must have its own inverse, and that inverse also must belong to the set S. And the fourth property is associativity. For any three elements A, B, C in S, AB combined with C will be equal to A combined with BC. This is called associativity. These four properties are called four group properties. I have already discussed one example of a mathematical group. There are many other examples. For example, let us consider the set of real numbers. The set of real numbers from minus infinity to plus infinity, including 0. This is a group under the binary operation of addition. If your operation is plus, then addition of any two real numbers will give you a real number, and therefore it is closed. 0 acts as the identity element because 0 added to A will give you A. So identity exists there. Any number A has its inverse minus A such that A plus minus A is the identity is 0, and therefore minus A is the inverse of A under addition, and associativity A plus B plus C the result of A plus B plus C is immaterial of whether you add B and C first then to A or A and B first then to C. So associativity also holds here. Therefore this set of all real numbers including 0 is a group under addition. But this is not a group under multiplication. Not a group under multiplication because this element 0 does not have inverse. Inverse of 0 does not exist on this line. Does not exist actually. But if you exclude 0, then it is a group under multiplication. Because the product of any two numbers, real numbers, is also a real number, and every number has its inverse under multiplication. For example, 3 is a real number, and its inverse 1 upon 3 is also a real number. Thus, this set excluding 0 is a group under multiplication, but it is not a group under addition. There are many more examples in literature, and most importantly, we will see that the set of symmetry operators of an object or a molecule is a group, and we will call such a group a point group. That will be discussed in a subsequent video. So, thank you very much for your patience.